Let's now turn our attention to interconnection networks. When more than one processor needs to access the same memory structure, you need interconnection networks to route the data. In the one case, you have the processors on the one side that are trying to access the memories, and because there's lots of processors, some of these accesses are going on concurrently. On the other hand, if we have a message passing multiprocessor where the processors don't directly access memory at the other end, you still need an interconnection network because you need to allow a way for one processor to get a message to another processor. And if you have a large system, you're going to need a large bandwidth because several of these transfers are going to be going on concurrently. Well, one way of doing an interconnection network is just to put everything on the same bus. And this, of course, has the advantage that it's pretty low cost. How does the cost scale as the number of processors increases? Well, it goes up at order n because you pay for each connection to the bus just about the same amount, so the cost is proportional to the number of devices connected. But how does the bandwidth scale? Well, that's not very good at all because as more devices get on the same bus, there is more contention. In fact, it's worse than that because the contention means that the bus spends more and more time trying to arbitrate among the various requests and less time transferring data, so the bandwidth actually goes down. Now, at the other extreme, for accesses to shared memory, the first kind of access is processors to memory that we talked about, the ideal structure is a crossbar switch, which has a connection directly from any processor to any memory. So you can see, for example, this processor accesses this memory by going over there and then transferring on down there, going to that memory. And ditto for any other processor memory interconnection. This allows all n processors to access all m memory units with an n by m crossbar switch. Now you can't have all of the processors access the same memory at one time, but you can have the processors all access distinct memories at one time. So any way that you want to arrange those distinct memories, basically any permutation of accesses from processors to distinct memories will be allowed. Since there are usually about as many processors as memory, then the complexity of the switch grows at order n squared. But what about the bandwidth? Well, the bandwidth only goes up at order n because you only have, your capacity only increases 1 for every item you add, so the capacity is proportional to the number of processors on the one side and the number of memory on the other side. So it just scales at order n. Now that's bad because it means your cost goes up at n squared and your bandwidth only goes up at order n. And so for reasonably large values of n, the crossbar switch may be more expensive than the processors and the memories. Of course, that would never do, so we're going to need to look for compromises between a shared bus and a crossbar switch. The analog of a crossbar switch for message passing is the complete interconnection network, which has a path from every processor to every other processor. Let's assume that the links are bidirectional. That means that, processor K can access processor N over the same link that processor N can access processor K. Now, how many bidirectional links are we going to need? Think about it. Each of the n processors needs to access n minus 1 other processors, but you don't need a link in each direction. You only need bidirectional links. So what you need is n times n minus 1 connections divided by 2 because the links are all bidirectional. Cost grows with the square of n, just like it does for a crossbar switch. As we talk about our various interconnection networks, we're going to use several metrics to describe their performance. The first is degree, and that's just the number of links or the number of wires, sometimes called edges, that are attached to a node. So if you have, let's say, something like a two-dimensional mesh, which I think we introduced on the first day of class, you can see that you're only going to have 4 wires attached to a particular node. Whereas if you have a complete interconnection network, then you have n-1 wires attached to a node, which is usually a much larger number. So that's degree. The second metric is diameter, which is the maximum number of nodes through which a message must pass on its way from source to destination. If it goes directly from source to destination without going through any intermediate nodes, then we say that the distance is 1. The diameter measures a maximum delay in transmitting a message from one processor to another. Well, that's kind of the worst case. The average case is also of interest. The average distance is the distance between two nodes, defined by the number of hops in the shortest path. And the average distance is given by a summation. The number of nodes that are at distance d from a node, n sub d, times that distance. So the number of nodes that are at distance 1 times 1, plus the number of nodes that are at distance 2 times 2, etc., up until we get up to the diameter, which is r. And so we take that summation, and that is the total distance of all of the nodes from the current node. We divide that by the number of other nodes, which is n-1, and that gives us the average distance between this node and all the other nodes in the system. The last metric we're going to talk about is bisection width, which is the smallest number of wires that you need to cut to disconnect the network into two equal halves. Okay? So in a mesh, we've got to make a cut, along one of the dimensions of a net mesh. If it's an n by n mesh, we're going to need to cut n wires. So that's one example of bisection bandwidth. But now for a crossbar, I'd like you to give all of these metrics: degree, diameter, average distance, and bisection bandwidth. Okay, well, which of those metrics that we've talked about are measures of performance and which are measures of cost? Degree obviously is a measure of cost because the number of wires that you attach to a particular node is going to be proportional to the cost of connecting that node. Diameter is a performance metric because it tells you how long, in the worst case, it takes to get a message from one side of the network to another. Average distance, similarly, is a performance metric because it answers the same question, but with respect to the average, not the worst case. Bisection bandwidth is actually also a measure of performance because it measures how easily you can get messages across congested portions of the bandwidth. Think, for example, of a tree. Near the root of a tree, you have only one wire connecting half of the nodes to the root. If that wire is severed, then half of the network is disconnected. So that means that a tree has a bisection bandwidth of 1. It's also bad from a performance point of view because all of the messages in one half of the network need to transit that single link to get over to the other half of the network. So any situation in which you have a very few number of wires that you need to sever to break the network into two, you also have a very small number of links that messages can transit to get to the other half of the network. So it's a metric of performance as well.